All right, folks, we are looking at assessing our least square regression model and deciding if it is a helpful tool, if it's an appropriate tool, and sort of just being able to be comfortable saying, hey, I found some stuff out, let's use it to predict, or maybe say, I'm not comfortable predicting. So the three tools we have today are residual plot, typical error, and what percent of changes in your y variable you can explain by changes in your x variable. So tool number one, to assess our least square regression model, I'm doing the height and hand span stuff, folks. This is for first period. So my first tool is to check the linearity. So when I said I see a positive, linear, moderately strong relationship between height and hand span, I'm going to investigate whether linear was the right thing to say. So I'm looking at a residual plot, and just a heads up here, the idea is your original x variable is on the x-axis, so that's height. And then you're going to transform your y variable into residuals, which we were calculating last week. But the idea with this residual plot is you're taking every single person's residual for their particular height compared to the line. So if we scroll back up to the scatter plot with a line on it, basically we're looking for every single vertical distance here and graphing that. And it's kind of like taking this positively sloping line and flattening out to be 0 and looking at those vertical distances. So you can kind of preview what it's going to look like here, just imagining flattening this line, flattening the line, and seeing how far away from the line every single dot is. And one thing that's going to happen is our y values will be smaller because they're errors. So if you go take a look at this residual plot, we have everybody's height and then how far off the line they were. So we have folks who have errors of like 1.5 and 2, but lots of people have small errors like a ½ inch or 1 inch. And then on the bottom, same deal, we have people with like ½ inch overestimates of their hand span and 1 inch overestimates. And then we have this kind of notable -3 residual. This one's kind of sticking out for you. The idea with a residual plot is it's zooming in on the line itself and helping you decide if really that was a straight line pattern. And so what you're looking for in this residual plot is random scatter. I think I see random scatter here. I'm a little concerned about the last three folks over here, our tall folks. We have one person whose hand is way smaller than expected, and then we have kind of a gap, and then we have one person whose hand's pretty close to the line, and then one person who looks like they're really close to the line, but actually what happened if you take a peek at the original graph, it's not so much that this person's close to the line, it's that the line came close to them. So when you have big gaps in the x direction, these points become influential. They drag the line towards them, and I'm curious about if that's happening for us. So I'm kind of curious about these last three tall folks and what they're doing to our pattern, but let's just go with it for right now. So I'm going to go ahead and say right here at the bottom that we don't do that, undo. Okay. So what I'm trying to do is have my text show up at the bottom of my graph. All right. We observe a random scatter in the residual plot. Sorry about the spelling, folks. This indicates that the scatter plot was in fact a linear relationship, and that using a least square regression line here is correct, because the scatter plot is in fact linear. Using a straight line to model that is great, and the residual plot shows us that. So I had some concern about the outlier, I had some concerns about the folks way over on the right, but that's kind of a different topic. So option number 2. The idea is when you're assessing your model, you're really using all three of these tools together to decide as a whole if a straight line model is helpful and correct. So option number 2, typical error. And the measure for that is S. And I'm going to show you how to get this on the calculator if you want. It's a bit complicated, but where it came from for me is just when I ran this statistical package and I got the equation of my line. It also gave me the s and the r squared, which we're going to use for our last two tools. So typical error s. So typical error s is the standard deviation of the residuals. And it's telling us that a typical error here is a 1.081. And if we were to interpret that in context, we are going to say that on average, the line makes 1-inch errors when predicting people's height. So on average, the least square regression line makes 1-inch errors when predicting handspan from somebody's height. Now the idea with this error is you would like your line to be making errors that are up to 10% of a typical y variable. So you want to take a moment and look at what kind of y values do you have. So an easy way to do that is to just look at your average y. A really generous way to do that is to look at your maximum y, which will give you a small percentage. So the question is this 10% error or less? If it is, then using the line is good and is helpful. And the way to assess that, I'm going to say our average handspan was 7.8 inches. This average error about, so we're doing 1.081. What percent of a typical handspan is that? So the error over the average handspan. And I got 14 when I did that. So 14% error. Now, that's a little bit more than 10, but it's not so far away from 10 that I'm like freaking out. So I'm going to say residual plot was great. I had some questions, but it's pretty good. Typical error is a little bit more than 10%, so I'm going to hold my judgment. So this is just telling me that when I'm estimating somebody's handspan, I'm going to be making bigger errors than I'd prefer. Right? And then I suspect that if everybody in first period had used more careful ways of measuring their hand, we would be having smaller errors. So everybody kind of went for whole numbers and inches, and that's pretty much why the error is happening. Okay, now our very last tool is the coefficient of determination, which is a very fancy. Now, how you get this, if you guys are interested in tracking what's in the textbook, it explains where it comes from. It's basically telling you how much better than not using the line is, all right? So if you didn't use the least square regression line at all and you were trying to guess someone's handspan from their height, you'd probably just guess the average height and the average handspan. How much better than just randomly using the class average is using the line. That's kind of what's going on here. What it really is just r squared. Damn it, where do I do squared? So I'm gonna fix that, make it pretty later. Okay. So r squared, it's literally coefficient of, it's the correlation coefficient squared. And the idea here is you want to capture at least 50% of the reason that handspans are changing. So for us, our r squared was 22.5%. We're going to say 22.5% of changes in handspan can be explained by, and there's a couple different ways to phrase this, can be explained by the least square regression line, can be explained by changes in height. That's the simple sentence, I like that one. 22.5% of changes in handspan can be explained by changes in height. So it means we found 22.5% of the explanation for why people's handspans are changing. So what I'm going to say is we are missing 77.5% of the reason handspans change. So we're missing a whole lot of the explanation. And so in our case, I'm going to say that this line is not nearly as useful as it could have been. Right? So I would say for assessing the model, sort of pulling it all together to assess the model, we have good residual plot, no concerns. Slightly large typical error from the line. A little bit of a concern, and very low coefficient of determination. That is my concern. That is the primary concern. So it was like no problem, small problem, and oh boy. So it seems that using the least square regression line in this data set is not that useful since we are missing a lot of explanation. And why handspans change. And like I said before, I think if first period had used more careful techniques for measuring their handspans, we might not be having this concern, but that's where we're at.